Okay, so last video we talked about relating the derivative to a spaceship, where the front of the spaceship was dy and the back of the spaceship was dx. And in each case, whenever we're always just talking about how high the spaceship is above how high the top of the spaceship is, and how far back the back of the spaceship is. So here the front of the spaceship was 0 high, because we're talking about where the front is in relation to the back. Here it was 2 high. We talk about where the spaceship was in relation to the back, and here it was 1 high. And the dx relates to how far back the back is. So here, from back to front, we had 1. Here, from back to front, we had 1, and here from back to front, we also had 1. So now we're going to take this analogy of our derivative and our spaceship, and apply it to a proper equation. And we're going to look at an equation today. We're going to look at this equation. We're going to look at y equals negative 0.1 x squared plus 2x plus 2. So this is a quadratic equation because it's got this squared term, so it's quadratic. And then we know it's got this negative. Because it's got this negative, it's got a sad face, because it's got a negative on the x squared term, so that's a sad face. And then we've got this 2 by itself, so that's the y-intercept. Don't worry about too much if you don't know these, but I'm just setting this up. So this graph's going to look like this. It's a sad face, it's a quadratic, and it's got a y-intercept of 2. So this is what it looks like. It's a sad face, because it's a quadratic, and it's got a y-intercept of 2. So we're going to consider 3 different points here. So when we talk about the spaceship launching, okay, so the derivative at any point on this graph, at any point of this on this graph, when we want to know about the derivative, we just imagine the spaceship taking off from the point. So say we want to consider the point. We can consider this point here. It's taking off from the point. The first thing. 2, it's got to be in line with the graph. So we're imagining the spaceship taking off from the point that we care about, and that point is the point that we want the derivative of. So imagine the spaceship taking off from the point. So if we want the derivative of this point, and it's got to be in line with the graph. So it's got to be perfectly in line with this graph. So our spaceship might look something like this, in this case. Right? So it's taking off from this point, taking off from the point 0, 0, it's got a straight line. 0, 2, that's this point, 0, 2, and it's taking off from that point, and it's in line with the graph where we start off. Let's consider another point. Let's consider if a spaceship was taking off from, say, 5, and it always takes off from a point on the graph. 5's here. 5, trace up, trace up, trace up. 9. So we're taking off, if we want the derivative at 5, 9, and just an aside here, this always goes x, y, and it's easy to remember the order of these coordinates because x, y, z, x comes before y in the alphabet, x comes before y in the coordinates. Okay, so that was just an aside, but so if we want the derivative at this point, we have to imagine the spaceship's taking off from here, and it's in line with the graph at this point. So at this point, if we were to draw a big line, it would kind of go like this, right? Something like that. If it was passing through exactly that point, a bit high. Yep, so that's in line, but the spaceship has to be taking off from this point. So we're just going to go like this, right? And so it's taking off like that. Taking off from the point in line with the graph. One final point we can consider. We can consider this point. Let's choose a different color. We've got green, we've got pink, let's go orange. It's taking off from the point, and it's in line with the graph. So that's our spaceship. It's in line with the graph at this point. So now that we've learned how to use we've learned the rules of using our spaceship, and what that dy dx is just asking us how high is the front of the spaceship and how far back is the back end of the spaceship. Now we've put these spaceships on a graph to find the gradient at any point, where we just have to imagine the spaceship taking off from that point and imagine it being in line with the graph. Okay, so that should be not too bad. So now we can actually look at these points and calculate it. At this point, I could say an important thing, and that's it doesn't matter how long you make your spaceship. Doesn't matter how long you make the spaceship. Okay, so don't worry too much about that. So first point we're looking at the derivative at 0, 2. When we say we look at the derivative, we're looking at the spaceship taking off from the point 0, 2, and we've got a bit of a zoomed in example here. So if we're here at 0, 2, when we want our spaceship to take off, it's taking off from here. 0 is the x value, 2 is the y value, and we're going like this. It doesn't matter how long our spaceship is, but it's got to be perfectly in line. So let's go like, let's just make it this long actually. So it looks pretty much perfectly in line to me. And I've got to say that this isn't a precise way of doing it, but right now we're just trying to get a feel. So it's taking off. So the question is, what is the derivative of our quadratic, which is y equals negative 0.1 x squared plus 2x plus 2. Remember that was the one we had up here, this one, and then it was this whole graph, and now we're just zooming in on a small section. So what is the derivative of this whole graph at the point 0, 2, where 0 is our x and 2 is our y? 0, 2. And all we have to ask is, well, how high is the front of the spaceship? Because the derivative is dy dx. We're thinking about a spaceship taking off. How high is the front of the spaceship? Well, to me it looks like it's, if we look at the numbers, that's 1. And if we look at, so that's 1. And then we look at this number, so we can put a 1 on the top. And then we look from there to there, and that's just a half, 0.5. 0.5, and so we have 1 divided by a half, and we have 2. So we can say, therefore, the derivative of y equals negative 0.1 x squared plus 2x plus 2 at the point 0, 2 is equal to 2. That's what we've just worked out. Now, let's illustrate this point of, so there's two different things we could do here. We could have either counted up the boxes, and so the number of boxes here, if I just copy this, and if we just look at the number of boxes, forget about the numbers for a moment, we can notice that the number of boxes here is 1 box, 2 box, 3 box, 4 boxes. And the number of boxes here is 1 box, 2 box, 2. So dy on dx equals 4 on 2, because the spaceship's head is 4 above and the spaceship's back is 2 behind, and that still equals 2, which is the same as that. So we can look at the boxes or we can look at the actual numbers. And again, I'll say it doesn't actually matter how long our spaceship is, because if we decided instead to draw our spaceship, say this long, right? That's how long our spaceship is. Then this length here is just 2, 4 minus 2, and this length here is just 1. So we've got dy on dx. The front of the spaceship is 2 ahead, is 2. The back of the spaceship is 1 behind, 1 equals 2. There's that 2 again. So all we have to do is draw our spaceship taking off. Don't have to worry about anything like what we're counting or anything, and we get the derivative. Let's consider another one. We're looking at pink at 0.59. So the point is 5, which is here, coming up to here, and 9. So the question is, what is the derivative of y equals negative 0.1 x squared plus 2x plus 2 at the point 5, 9. 5's our x, 9's our y, x, y, z in the alphabet. And so all we have to do, we know the rules by now, you just have to launch your spaceship from here, and it has to be perfectly in line with the graph. So I'm going to go like that. That looks pretty in line with the graph to me. And then how high above is the front? Let's just count the boxes. It's just 2. How far is the back? 2. So we can go dy over dx equals 2 and 2. 2 divided by 2 equals 1. So our solution, therefore, the derivative of our graph equals negative 0.1 x squared plus 2x plus 2 at the point 5, 9 is equal to 1. Okay, so that's that. And now we've got one last example. When we're just looking at this top, we're looking at this point, which is 10 and 12. X, Y, Z, X before Y. So we've got 10, 12, and we're launching our spaceship. It's got to be in line with the graph. Doesn't matter how long it is. And so how high is the front of the spaceship above the back? Well, it's 0. This is the same as the example we saw in the first case. Remember, this was 0. So our question is, what is the gradient? Gradient and derivative are the same thing. So gradient equals derivative. What is the gradient? Let's just put in brackets, of y equals negative 0.1 x squared plus 2x plus 2 at the point 10, 12, x before y. And so we know we're finding the gradient or the derivative, dy over dx. How high is the front? 0 high. How far back is the back? We can either count boxes, which would be 1, 2, 3, 4, 5, 6, 7, 8, or we can just look at the numbers. 10 to 14 is 4. So 0 divided by 4 is 0. So our conclusion is, therefore, the derivative of our graph, which is y equals negative 0.1 x squared plus 2x plus 2 at the point And you can be thinking about what, hopefully you've picked up what this sentence is by now. The derivative of your graph at the point, what am I going to say next? 10, 12. What am I going to say next? Is equal to, what's it equal to? 0. So that's 3 examples of how we can use the rocket ship analogy to think about what the gradient is at 3 different points on this quadratic. All you have to do is think about where's the spaceship taking off from, and then do your dy dx. How far is the spaceship's top above the back of the spaceship? In the next video, we're going to link this through with we're going to bring it into calculus and make that connection.